All right, in this lecture, we are going to talk finally about fiber bundles. Very important concept that sort of bridges the gap or bridges the span between elementary general relativity and intermediate general relativity. We've learned about differentiable manifolds, and that is what it takes to create fiber bundles. And there's a lot of way of approaching how to understand fiber bundles, and the typical way is to, or atypical way is to just sort of present the hardcore definition of what it is and then start showing examples. And the alternative way is to sort of work with an intuition of what it could be and then try to get to a hardcore definition. I think I'll take the second way because there is such a nice canonical example of a fiber bundle that illustrates so much about what it is that it's really hard to resist talking about it. And that is the cylinder. So I'm going to present a cylinder, and I'm going to make a unique or a special mathematical construction for a cylinder, and slowly we'll generate and understand what a concept of a fiber bundle is from that. So beginning with this idea, let's take a look at a cylinder. Now this is intended to be an infinite cylinder, so it should go up forever and down forever. And in the middle of the cylinder, I'm going to outline one particular circle, which is a cross-section of the cylinder. The cylinder is hollow, by the way. This is a hollow cylinder. So I'm going to just take out one particular circle in the cylinder, and I'm going to call that circle S1. And the reason I use S1 is the class of all the spheres is always accompanied by dimensions. So a one-dimensional sphere is S1. Two-dimensional sphere, which would be the surface of a ball, is S2. S3 would be the three-dimensional surface of a hypersphere, etc., etc. So S1 is just a circle. All right. So with S1 in place, then every point on the sphere or on the cylinder, and I'll make a point, say this point here, that point there can be understood with its own in a coordinate system, right? The surface of the sphere is, in fact, a differentiable manifold. So we can imagine a coordinate system, and the easiest one to imagine is associating that point with a point of the circle, a point of this circle, and some sort of height above the circle. And if we take the height at the circle as, say, 0, then this might be positive height this way and negative height that way. So every point on the sphere will have some member of S1. So I'll say it'll be two coordinates, A and B, where A is an element of S1 and B is an element of the real numbers. And so I can create this ordered pair on the surface of a cylinder, identifying every point on the surface of a cylinder. The coordinate in A in S1, it just has to be a number, for example, between 0 and 2 pi. Well, actually, including 0, it's 2 pi. What am I doing? A number between 0 and, say, 2 pi. Anywhere in that range could be a number for A, but in fact, it could be any number. It could also just be any real number as long as we understand and identify all values of 2n pi, where n is an integer, right? If we create that identification that all 2n pi values are equivalent, then I can create a coordinate system on S1 that's essentially the same as the real numbers in many ways. I'm not going to go into that. This is an important subject about that basically touches on the notion of quotient spaces. Quotient space. And that's an important subject. We will definitely have to get to that eventually, but not right now. In fact, some of our examples will do it. Maybe I'll do it when we touch on some of our examples. But so I can now create this ordered pair for any point on this cylinder. What's interesting about this is I can break this cylinder down into 3 separate differentiable manifolds. This one, the whole cylinder itself is already a differentiable manifold. I'll call it E. and I'm going to call the E, and that we're going to learn eventually is called the total space. But as we can see by the way we've constructed this, I also have this S1 involved, right? And I also have this real numbers involved. The S1 I'm going to call the base space, and the R I'm going to call the fiber. And basically the idea now is that this total space can somehow be understood as having part of its basic structure two other differentiable manifolds, the base space and the fiber. All three of these are differentiable manifolds. So I have these three differentiable manifolds. But what makes this important is that I can actually, for a given point, I can write down that point in the total space using this ordered pair in the case of the cylinder. And the ordered pair cleanly places every point in the total space as a point that has a specific piece of the base space and a specific location in the base space and a specific location in the fiber. And I can take those two and create this ordered pair of points. So in this particular total space, every point can really be thought of as a member of the base space in a sense and a member of a fiber in a sense. So it's not really a member because it as an ordered pair is just an ordered pair of elements. The point is an element of E. It's not even an element of S1. It is an element of R, but it's not an element of R in general. It's an element of just the R that we can associate with that particular A. And that's what's so important here, is that what I'm really looking at is S1 Cartesian product R. That is the way E is constructed. And by definition, you can see I took the total space. I just took the base space that the point was lying over, and that became the first part of the ordered pair, and the second part of the ordered pair became the real number on this line. So that's the definition of what this is. This is defined as the set of all ordered pairs A and B, such that A is an element of S1 and B is an element of R, right? So in this particular case, I've actually created E as a set, a Cartesian product set. And you think, well, no, it's a cylinder. It's not a set of ordered pairs. But in fact, this set of ordered pairs and this geometric cylinder are in one-to-one correspondence. It's the same thing. And we basically say this is the cylinder. This is the cylinder. And so what's very nice is we've got these three things, the total space, the base space, and the fiber. But they understand that this fiber is a general fiber because that particular fiber, the one that's associated with the point A, is not really the same one as this one over here, which is associated with, say, the point Q, right? That's a different fiber. On the other hand, it's very much the same. They're both R. It's just a different R because this R is attached to that particular element of the base space, and this R, real number line, is attached to that particular element of the base space. So when we speak of the fiber, it's a bit ambiguous when you're first learning this because I could be talking about the fiber at a point, in which case I'm talking about one particular fiber, or I could talk about the generic fiber for which all of these are identical copies. And that's really important. That's part of what makes a fiber bundle, is that this Cartesian product, it has one classic base space, but all of the fibers for every point are all diffeomorphic. Because remember, the fiber is a differentiable manifold, so every fiber here has to be diffeomorphic. So I may choose, for example, a totally different coordinate system on this fiber than this fiber, but they better be diffeomorphic. The two fibers better be diffeomorphic, and in this case they clearly are. So that's pretty good. there is a question of the topology of all this, right? Because E, the total space, is this thing. Well, this thing is a Cartesian product. Well, the Cartesian product of two topological spaces is a topological space, and it is because it is if we apply a topology, right? It isn't automatically a topological space. That's a good point. Let me be very technical about that. This as a Cartesian product is a set Cartesian product with another set. This set comes with a topology, but that's not what this means. This just means the Cartesian product of the set, of the circle set with the real line. The resulting set E does not automatically come with a topology, but there is a topology we could give to it very easily, and that's called the product topology. And the product topology is just the product topology on E. If we wanted to give E the product topology, it turns out we will not. But if we wanted to, it's just going to be the set of UI Cartesian product Vj, such that UI is an element of the topology of S1 and Vj is an element of the topology of the real numbers, right? That if these are defined as the open sets of E, you'll have a topological space for E. You could do that. Now, it turns out that we don't do that. We don't, first of all, we haven't defined a fiber bundle. Let me make that clear. All I've done is talked about a couple differentiable manifolds and a Cartesian product. The topology that we're going to choose for E in this case, or in any case, is not going to be this topology. But the point is E can be made into a topological space very easily by applying this topology, the product topology. So, but let's keep moving a little bit more towards our definition of. We'll talk more about the open sets in a moment, but the open sets on E in a moment, or all of these spaces. We have to define the open sets on all of these spaces. I just said they were differentiable manifolds, so you know that they all have their own topologies, right? We just haven't described exactly what these topologies are right now, but by definition, they're given as differentiable manifolds. So anyway, the other thing that's kind of interesting to note here is that given a point P, I can always assign it a point in the base space. So given a point P in the total space, a point P in the total space can always be assigned a very simple way a point in the base space. And with the cylinder, it's very easy to visualize this. And that's why it's a useful tool to get started. But in most general fiber bundles, this process of projection may not be so easy to see. But this is a good example to start with. And what we want to do is we want to kind of project down as sort of the theory. So how do we kind of formalize that? Well, the first thing is we have to create the projection map. And in this case, the projection map is always called pi. For fiber bundles, it's always called pi. And the projection map is a map from the total space to the base space. And that's going to project. So I take any point out in the total space, like P, and I project it into the base space. Now, in this particular case, because E is this Cartesian product, this map is very easy to understand. I just take the point in E, which is an ordered pair by the definition of how it's constructed, and I return A. And the reason I return A is because A is the element of S1 that corresponds to any points P's coordinates. So that's good. But the thing that makes this important, or the thing that's important to capture here, is that the inverse map of a point A in the base manifold it's going to equal a set. It's this mapping here is many to one. So therefore the inverse has to be one to many. And in this case, that one to many is going to give you this real line, because anything in that real line projected under this rule is going to return A. So the inverse mapping, or the pre-image of A, has got to be this entire line. So be it. The inverse mapping of A must be the real line. Now specifically, it must be the real line at A, right? Because there's actually a real line here at Q too, and a real line at T and R and B and S. So every point over the base manifold has its own real line. So this inverse mapping has to be, it's the real line at A. But what's also important is if I take the inverse mapping at Q, right, and say Q's on the back of the cylinder, say I project Q, so pi, and I'll say that's A, B, let's say C and D, say Q is located at CD. Well, pi CD is going to be C, and pi inverse of C is going to be the real line at Q, which is not the same as the real line at A. It's a different set. But what's critical to make this a fiber bundle is this inverse projection mapping. These two things must be diffeomorphic to the real line in general. They're both diffeomorphic to the real line. So whatever you land with, this thing has to be diffeomorphic to what we are calling the fiber, right? Now in this case it's easy. You've got a real line and a real line, they're diffeomorphic to each other, and they're certainly diffeomorphic to the generic real line. In other circumstances that won't be so clear. And but this process here, because of this structure, this process, it is clear, and it's called trivial, right? It's called trivial because this entire thing is, the entire total space is simply the Cartesian product of S1 and R, right? But what's important is that the pre-image of any point from the base space has to be a set that is diffeomorphic to what we're going to call the fiber, or the generic fiber. So this is the fiber at A, the fiber at A, this is the fiber at, I said Q here, but it should be the fiber at C, right? This is the fiber at C, and those two have to be diffeomorphic to each other and diffeomorphic to the generic fiber, right? So that's important. Now I should say that at this point we have virtually established everything we need for to define a fiber bundle. Not quite, but it's very close. And ultimately, the fiber bundle is three manifolds. B, well, let's start with E, the total space, B, and F, the fiber. Actually, I'm going to rewrite this and put it over here. E, B, and F. And we also have this projection, which is a projection from the total space to the base space. And we have the inverse projection of a point in the total space must be diffeomorphic to the fiber. And once we start doing that, once we've got that, we've got almost everything we need for the fiber bundle. So why don't we just sort of express this in a little bit more mathematical terms and get at the difference between the trivial bundles and the more sophisticated bundles. So I'll start by drawing the space E, which is the total space, and the base space B. Notice the base space is not a subset of E. It would be incorrect to think of the base space as a subset of E, even though when you think of the cylinder, it kind of feels that way, right? Because you got this circle. But remember, E is, the way we've defined it here, it's B cross, or B Cartesian F. That's a set of ordered pairs, right? The set of points here are not a set of ordered pairs. There is a set of ordered pairs where all B equals 0, so it's A, all points A and 0. But that is not the base space. The base space is just the set of points on a circle. So it's important not to think of the base space as some sort of subset of the total space. The total space is its own thing, or I prefer to think of it that way. And we have the projection, pi, and the inverse projection, pi inverse. And what we know is that any point in B, a point P, will land over here in E, and it lands as a full-size set somehow, and that full-size set is ultimately isomorphic, or I keep saying isomorphic, but I mean diffeomorphic to the fiber. I'll make the fiber a little triangle. And so this region here is pi, is the projection, inverse projection, or I should say the preimage under the projection of the point P. And the preimage of the projection under the point P, there is diffeomorphic to the standard fiber. That means there's yet another map involved. Another map is involved to get from whatever is in E, but it's a very tight map because it's a diffeomorphism, which means it's one-to-one, it's on two, it's continuous, it's bicontinuous, and all of that. So with this in mind, we have now repeated sort of in a general terms what we're after for at least some of what we mean by a fiber bundle. But unlike the cylinder, where it was very easy for me to take the base space and build up the cylinder immediately by applying all the fibers and universally deciding that E is simply the global Cartesian product of a circle and the real numbers like that, we can't always do that. We can't always do that. And what we can always do, however, is for any given subset of B that is part of a cover, so I'll call this subset UI, and the set of all the UIs is an open cover of B. And using these open covers of B, I can demand, well, first I need to demand something about the topology of E. I guess that's an important point first. Any open set in B has a preimage in E. And this is just the preimage of a point, right? This set here is a preimage of a single point. But a single point is not an open set in B. We don't use the discrete topology where every point of B is its own open set. B is going to have some other topology. It's typically, in the case of the circle that we used, in the case of S1, that topology were just these open intervals all around the circle. And or that would be a base of the topology, these open intervals around the circle. So any open set of B, the preimage of that open set has got to be an open set of E. And if that was not the case, then pi wouldn't be continuous. Because remember, the definition of continuity for a map is the preimages of open sets under that mapping must be open in the domain. So the preimages of the open sets of the range must be open in the domain in order for the mapping to be continuous. So the continuity of the mapping, remember, always sort of leans on the behavior of open sets under the inverse mapping. So in this particular case, if I take an open set here in UI, over here I'm going to get some set in E, and that set is going to be pi inverse of UI. And that is going to be open in E because we are defining the topology. We are defining the topology of E to be the set of all the preimages such that UI is an element of the topology of B. So all of the preimages of the sets UI, where UI is any set in the topology of B, the preimages are going to be thrown into a bin, this set, and that's going to be the topology of E. I'll let you prove that this is a topology, but it is. It's actually a relatively coarse topology. It's not as fine as topology. You could, like for a cylinder, if you look at it in the context of the cylinder, what you'll discover is that the open sets on the cylinder under this rule are these infinite strips or those would be bases for the open sets, these infinite strips. So unions and infinite unions, or finite or infinite unions, and finite only intersections, those infinite strips, that would be the topology of the cylinder under this rule. And it's coarser, right? It's coarser than, say, any region on the surface of the cylinder, which would be a much finer topology. But this coarse topology is good enough because it makes the projection map continuous. So that's fine. And we don't have to impose any stricter topology on E for our purposes right now. I will now erase this. But let's see. So with this inverse image of an open set in B, we get this open set in E. This is part of a cover, right? It's not the whole set. It's just part of a cover of the set, and it yields us an image over here. Now, in order for everything to be a true fiber bundle, this image here now has an obligation, and that obligation is that it has to be diffeomorphic to UI Cartesian the fiber. There has to be a diffeomorphism from there to this trivial construction here. And I'll draw this isomorphism with these arrows like this. This is what makes any given set E locally trivial. That means I go to any little region of E that's open in E, right? And it's open through this diff. So I know if it's open in E, it corresponds to the pre-image of some open set in B. Any region that's open in B, I know I can make a trivial, or I can make a diffeomorphic mapping to nothing more than the open region in B Cartesian product with the generic fiber F. And this mapping here is very, very important, and it's given different names in different books. So let's cover what some of those names are, just in case you study this in other books, and I recommend you do, of course. The one common way is to give that mapping a name, capital, I guess that's capital phi sub I. And you need the sub I because this mapping only applies to the region UI, that one part of the open cover. So what I'm doing now with this definition is I say, well, I've got my trivial structure, and I can map that trivial structure right into the total space, and I can project it, and I get back UI. So this section of the total space is diffeomorphic to this trivial thing, this trivial object. The way I learned it was with a different notation, which is actually a lot more complex. The map is actually called pi psi, and it doesn't go from the trivial Cartesian product to the total space. It goes from the total space to the trivial Cartesian product. And so phi is this thing's inverse. But this is just two different notations for the same diffeomorphism, right? This notation goes in this direction and is written as some kind of pair of things, which I'll talk about in a moment. And this notation goes in the opposite direction, and it's given an index attached to the open region. This one is also attached to the open region. You have to do that. You have to be attached to it, but it's just given its own little letter. The pi, of course, says that that whatever this is, it's bound to the base space through pi. It's like extra information. There might be 2 or 3 different projections. You would never know with just looking at psi. But here, I guess, the ambiguity of the projection is eliminated by actually placing the projection in the name of the map. So this thing here is to be understood as the name of a map. And then this thing here would actually be, I suppose, pi psi inverse. And this thing would be pi I inverse. So this is 2 different notations I'm using, right? 2 different notations. I like mixing notations. It's just something I like to do because I read so many different books on this subject that sorting through the notation frequently is how I actually learn things. And years ago, I definitely wrestled with this, and even reviewing it, I had to kind of sort through the notation. So you might ask, well, okay, so yeah, it's different notation, but what's this phi actually, right? That's an important question. What is this phi actually up to? And phi is a mapping from E to F. This thing here is essentially phi. Phi is a mapping from the preimage of the open set of the cover in B. That preimage gets mapped to the generic fiber. And that's what phi is. So I can put phi right here also. So it's only this other mapping, that sort of the mixture of phi and the projection, that we're calling this a diffeomorphism onto this trivial structure. And that is this diffeomorphism, this notion of being locally trivial, meaning the preimage of anything over the base space. This is sort of over the base space, right? Because it's the preimage under this projection. So all of this stuff would be projected onto this region of the base space. So this is the region over the base space. So the preimage of the base space, that preimage is always going to be diffeomorphic to this trivial structure. And the reason this is important to talk about it over certain areas in the base space is because there is inevitably going to be another area in the base space, and it's going to have inevitably its own preimage, and that preimage is also going to be diffeomorphic, but under a different mapping, because that preimage is going to have its mapping to the fiber bundle might be phi, and its mapping to UI, it will have a mapping not to UI, but this would be, say, UJ. It will go to UJ across the fiber, and that mapping will be pi phi, like that. And every region of B is going to have that kind of structure. And in the end, we're going to use the exact same language we use for differentiable manifolds. We're going to call this, well, we're going to call this thing here is going to be called a bundle chart. Or it's also called a local trivialization. But it's a bundle chart, and this is the base region of the chart, and pi inverse gives you the total space region of the chart, and then psi ultimately helps you construct the connection to this trivial space. And the problem is I can create a bundle chart for this guy and a bundle chart for this guy, and the two regions here are going to both be diffeomorphic to this trivialization of the underlying portion of the cover with the fiber, but this region in here where they overlap, right, this overlap region, which I guess I'll mark in green, which in this case includes, well, the way I've drawn it over here, it includes P, so let me just move P into the intersection like that. And this region here, this region is locally trivial to this Cartesian product and locally trivial to this Cartesian product. That's not a problem. Those are really the same thing, but they have two different mappings to get them there. So the two different diffeomorphisms are the problem because they don't have to agree, meaning a point in the intersection under this diffeomorphism could land in a completely different place here as it does here. And so now we have to understand that this wouldn't be a problem if you could just take the whole manifold B and just create one well, there's only one projection map, but you take that whole manifold B, and that projects into, fills up the entire total space, and then there's only one mapping. If you could do that, that'd be no problem. That would be globally trivial. Locally trivial means you can't do that. You can't find such a mapping. And we'll show examples of this next time, but in this case, you can find it for every local region, and then the question is how do you handle these regions where they intersect? So let's talk about how you handle these regions where they intersect, and then that'll be our final topic for today, and then our next lecture will be a specific examples of how to build a structure like this using some pretty common ideas from physics and mathematics. I guess ultimately another important way of looking at this is locally any point in the total space can be expressed as essentially a coordinate in a sense, but a pairing of a point in the base space and a point in the standard fiber, because this is ultimately if nothing more than an ordered pair, right? Where A is in UJ and B is in F. But I can do that locally in E, anywhere, I can do that locally. And in places where there's overlaps, there's two different ways of doing it. Two different ways of doing it. And so I have to resolve overlaps, right? I have to establish a connection between here and here. And that is going to be the next step. But this is very much like manifolds, where I have the same issue. At any point in any region on a differentiable manifold, I can give it coordinates, and those coordinates have to be reconciled. But this is not quite the same as coordinates, right? This is saying I can actually give every section of the total space this kind of structure, and I can locate any point in this space with by knowing this structure. And because any point can be diffeomorphically connected to this structure, I can do this projection process by just eliminating the fiber part of the structure. I can get this projection process over with pi. And by really adding the fibers back, I can get this inverse projection and go from the base space to E. That's the part that makes a fiber bundle different than just your normal differentiable manifold. Now, the fact that E has this topology that we spoke of will also allow E to be a differentiable manifold in its own right. So that's an important point too. But the next thing we need to do is talk a little bit more in detail about these intersections. So let's do that. I can't resist saying when we deal with E as a differentiable manifold, we have to remember that this implies all of the normal things we would expect from a differentiable manifold, even though it has all this extra structure that has to do with the being a fiber bundle. In particular, every region of E that is part of its chart, it has, remember, E has its topology, which we've decided is the initial topology, and it has its atlas. Well, every chart in the atlas, UI, UJ, we already know that every one of those charts has its own chart map to RD. That is completely different than going back to the base space, taking a cover from the base space, which I'll call, say, VI, inverse mapping that base space region into the total space, right? That, and then taking that and mapping that diffeomorphically to VI Cartesian F, right? This is a chart mapping called a bundle chart. This is the manifold mapping, the regular atlas, because E is its own manifold. I can put coordinates down on E using the fact that it's a differentiable manifold, but I also have the ability to do this other kind of structural design with the base space and these mappings here. This mapping was the one we were calling pi, and then I think I called it psi, right? But or it was phi I if it went that way, right? Depending on what book you're reading, right, or what notes you're looking at. But regardless, this diffeomorphism, this is why fiber bundles are different than regular differentiable manifolds. All differentiable manifolds have this. That's what they are by definition. This is the fiber bundle structure that is so different and important. Okay, so about these overlaps. All right, so let's begin this by understanding exactly how we might take the points in the total space E and express them in terms of, say, UI cross F, which we'll create in a moment. So we got to start with a point in E, call it P, and the first thing we have to do is we have to go back to the base manifold. And so I'm going to find the point pi of P in the base manifold, which is a simple projection using the continuous function pi. And of course I have pi inverse. Pi inverse is very important. So that's the projection map, which we know we have because we're presuming this is all a fiber bundle. So once I've created this guy, pi of P, then I'm going to create a neighborhood around P, which I'll call UI, or around pi of P, which I call UI. And that is one of the members of this cover of B that is associated with a bundle map, a bundle mapping, or a local trivialization. So then I take that object and I project it back through pi inverse, and I get something around P over here, which is pi inverse of UI. Now I have a neighborhood around the point P in the total space that is connected to this bundle chart, this local trivialization. So what does that mean? Well, that means that I can, by definition, what that means is that I can take this neighborhood and create a diffeomorphism to UI Cartesian F, which is the set of all ordered pairs A, and I'll make little f. Well, actually, I'll do it differently. I'll do it B and little f. And the reason I'll use B is an element, little b is an element of big B, and little f is an element of big F, where big B is the base space and big F is the fiber. So I think that's good. And I know that I have this mapping because we've given this mapping a couple different names. I hope I'm not confusing you using two different names. I find it less confusing to have more symbols. I realize that's a bit unconventional, but I don't know why I'm okay with it. So the mapping with the big name phi I, right, goes this way, and then the mapping that's called pi psi goes that way. And now I can take P in the total space and map it this way, or use the inverse mapping of psi, depending on the notation I'm using. It's the same diffeomorphism, by the way. It's just a totally different notation. And just to be clear, this is literally equal to psi I inverse, and this is literally equal to pi psi inverse. And as a reminder, this ordered pairing pi and psi, it's intended to be the name of a map, right? So it looks like an ordered pair, but it's the name of a map. It's not like this ordered pair here, which is actually an ordered pair inside this set, right? That lives inside this set, the Cartesian product of UI and the fiber F. And I guess for good measure, I'll put out a set over here, which is literally the generic fiber F, and the map psi itself actually goes right to it. You know, this here should be a psi. The way I've drawn it, it kind of looks like a phi, but I want it to be a psi. Okay, so now that is the procedure for taking a point in the total space and expressing it in terms of this ordered pair in the local trivialization. And this whole process is this is a local trivialization of this region of the total space. That's what this is. And it started by taking P, projecting it back to the base space, finding a bundle chart. So you're finding a neighborhood basically of P that neighborhood has to be associated with one of these things, and that combination is a bundle chart. I suppose we could make this even more look like a bundle chart, look like more like a manifold. If I say UI, I guess I could do it two ways. I could say UI phi I, right? That is a bundle chart. Likewise, it would be UI psi would also be essentially a bundle chart. And the reason the reason for this psi instead of the reason of putting psi in there instead of this is because this already exists no matter what, right? It's not it doesn't add any information to the nature of the chart, but this is actually unique to this chart area. So we would throw in the psi there. But those would be bundled charts, and I put them in a set, and that's probably a mistake too, right? Because when we look at these things, well, let me erase them. When we look at these things, the chart itself is just one pairing of UI psi I or UI phi I or UI psi, like that. The problem with the second notation, by the way, is there's no explicit, in the books that I've seen, there's no explicit index here. So you just kind of have to know that psi is connected with UI. And the reason is because they only play usually with two of them, like we're going to do in a minute, and it's easy to keep track. I got to say I'm leaning towards this notation a little bit more the more I look at it. Okay, so this is basically the idea of, it's a repeat of the idea of a bundle chart. And so what I've done is we've started with a point. The point is this is a differentiable manifold. So it has its own coordinate system. So P has some coordinates in some chart mapping in E. And that's totally irrelevant for what we're talking about. That has nothing to do with it. It is a differentiable manifold. It has an atlas. That point has a coordinate in R of whatever dimensionality of E is. But I take that point, I project it back to the base space, and then I find that neighborhood, go back and find the surrounding neighborhood, and it has its bundle mapping into this trivialization. Therefore, I can give that point a different type of coordinate. I can give it a coordinate associated with one point in the base space and some point in the generic fiber. And that also identifies and locates that point. Right? It doesn't have the benefit of all of the full-on topology really that we had before, but it can be given that. And this satisfies the sense of a coordinate. Okay, so now let's look at this with the idea of two charts, right? And you can see what's going to happen. We're going to have a second, when we went back here and we picked UI, I could have picked UJ, and UJ and UI are not the same. They both will have P in it, but they're going to have different mappings into the Cartesian product. They're going to have different trivializations. It's not going to be psi. It's going to be like phi or something, little phi. And its capital phi j is going to be different. So getting from P into here will give you a different BF, a different ordered pairing, because you're using a different trivialization. Now for the cylinder, there was only one UI. We took the whole circle. So the entire set was one big bundle chart. And because of that, there's really only one map. You can't find a different map using the way we did it before. So there's only one phi I because the entire space E is trivial. The entire space E is trivial, so and that's reflected by the fact that I can take the entire set B as the neighborhood UI and go to and project backwards into the entire set E, right? This pi I of ui would have been the whole set, and therefore there would have only been one local trivialization, and we would have been done. The problem is you usually can't do that. And so now we're going to look at what happens when you can't do that. Okay, so this requires blowing up the picture a little bit. So we'll start by looking at u sub I in the base space. Right, so this is all the base space over here. And u sub j, and then over here in the total space we will have a point P, and therefore over here we have a point pi of P, the projection of P down in the base space. So that all depends on the mapping pi, the base space F. Everything makes sense so far. Now we do is we can project both ui and uj into the total space using the inverse projection mapping. So if we did that, we would end up with here, which is inverse projection of u sub I, and likewise we would end up with this, which is inverse projection u sub j. And of course we're going to start focusing on this intersection region, right? That's going to be important. So because we're dealing with a local trivialization or a bundle map, those are synonyms, right? A local trivialization and a bundle map would be, I guess if we tried to use our sort of our manifold language, the pairing u sub I with phi sub I would be a local trivialization, or likewise the pairing u sub I with what we call pi psi. That would also be considered a local trivialization. It's the same concept, just a different way of naming the maps. But in order to make that work, I'm going to just focus a little bit on this region here, right, which would correspond to this region here. And that region we will call that u sub ij, right? And then likewise, of course, this region here has to be called pi inverse of u sub ij. Okay, but there are now two different local trivializations that will take this pre-image of that intersection, one local trivialization and another local trivialization. And one of them would be called pi psi, and the other would be called pi phi, and they both land in the set uij Cartesian with the fiber. So they both go into that same set. And these functions would also be called, I guess the way I'm doing it, phi I inverse and phi j inverse, depending on the notation you use. Now the phi and the psi alone, the only difference between these notations is I've got a phi and a psi alone. Well, all that is, and it's confusing because there's a lot of things, but I think ultimately understanding it reduces the confusion. I'm going to slide this over. P, the point P, or any point inside that set, will be mapped by psi and phi, but it won't be mapped to this Cartesian product. It'll just be mapped to F itself, which I'll sort of draw as a triangle, I guess. Right? So the point P will get mapped to two different points in F itself. So all this is if I stick with psi and phi, all I'm doing is getting rid of these base points and considering this region as being mapped into F itself directly. And that's not a problem, because even if I execute this mapping, I can just execute another mapping where I just erase that and I can map it directly to F by projecting out the first part of the ordered pair, right? So in other words, each point in here is an ordered pair AB, where, well, how about I even make that clearer? It's BF, where B is an element of the base space and F is an element of the generic fiber. Well, I could just create a mapping to F directly by simply taking BF just to F, right? So there's these things, there's just different ways of expressing where you want to go from the total space, but ultimately you end up in the same place, because the only difference is whether or not you're going to carry around the base point. But the bottom line is that any point inside this intersection can be mapped directly to the fiber, and each local trivialization will map each point in the total space to that fiber in a different way, unless your total space is so simple that it can be written simply as the base space Cartesian product with the fiber, in which case you only really have one massive local trivialization and there's only one map, right? So any second map would just be the identity. Now any second, there's only one. I can make it so that I take the base space, and instead of creating two, all I need is one. The total base space is the neighborhood of the point. I map that under the inverse mapping. I get the complete total space as the inverse mapping. The pre-image of the base becomes the total space, and then there's only one map. I can, under the same circumstances, the same mathematical structures, I can still split the base space up into two different bundle charts, and I can still map it to E, to covering the whole E and with two different bundle charts, and I can still create two different mappings into F. However, in the end, mathematically, that shouldn't be any different, and I have to articulate why it shouldn't be any different, right, if I did that, as long as the total space was trivial. The point is, if the total space is not trivial, then I must have more than one bundled chart. And the transitions between these, as we're going to see in a moment, will be more sophisticated in that case. So, but the idea is, what is this transition function? Well, very much like manifolds, we are interested in going from, if I land in this point using one chart, how do I know what that point was using the other chart? And it's pretty simple. I need to have a map from F to itself that converts the F that is generated through the phi mapping. I have to be able to translate that to the F due to the psi mapping. And it's pretty easy. It's going to be psi inverse compose, or it's going to be phi inverse compose psi to, or likewise it's going to be psi inverse compose phi, right? And those will be mappings from F into itself. Likewise, I could use, if I'm using this other notation, I'm interested in mappings from this trivialized Cartesian product space into itself. And those mappings are equivalent transition functions, just written in terms of these guys here. So, but again, those are really the same mappings. And ultimately, even when I create those mappings, all I'm really interested in are mappings of F into itself that can convert the two different local trivializations into one another. So F is a differentiable manifold, and any mapping from F to F is going to be, any mapping that we care about, is going to be a diffeomorphism. Right? It must be a diffeomorphism, and that's not too hard to see. these are diffeomorphisms, these are diffeomorphisms, so their composition will be a diffeomorphism. So these functions here are in fact diffeomorphisms on F. And that's important because there's a group out there called diff F, which is the set of all diffeomorphisms from F to itself, right? And these guys here must definitely be members of that group. And in some sense, I'm expressing the difference between two local trivializations in terms of various diffeomorphisms in the group F. So so ultimately, that's a requirement for a fiber bundle, is that all of these transition functions must be diffeomorphisms on the fiber itself. And so now that's the last of the properties we have to understand. So if I wrote down the properties for a fiber bundle, I would say you need a total space, a base space, a fiber, a projection, and then there's those rules on the projections, right? Which is that the inverse projection of a point B in the base space must be isomorphic to the fiber, and I also have to have this notion of all of the transition functions must be diffeomorphisms on F. Now, the last part of this is a bit tighter, because if I build a fiber bundle and I've got all of this stuff and I look at all of the transition functions of my fiber bundle, those transition functions will by definition be members of the diffeomorphism group because they will be diffeomorphisms. I need to tighten it up just a little more because I need to assign to this collection of properties, I need to assign to it something called the structure group. And the structure group is a collection of diffeomorphisms, a subset of these diffeomorphisms that applies to the fiber bundle I've designed. And every transition function must be a member of the structure group, and every member of the structure group must be a member of the diffeomorphism group, but the structure group is much smaller than the diffeomorphism group. In the case of the trivial or the globally trivial cylinder, the structure group can be made as small as a single element, the identity. Because ultimately, no matter how many regions, no matter how many charts I put on the cylinder, if I'm clever enough, I can design them so that the transition functions are all the identity element. For the Mobius strip, and which we'll see next time, I can't do that. I can make most of the transition functions the identity element, but at least one of them is going to be multiplication by -1, for example. So the structure group for the Mobius strip is going to be 1 and -1, or the identity and then minus the identity. I'll build that up next time. But the final definition of the fiber bundle demands that we not only provide the total group, provide the base space, provide the fiber, provide the projection, demand that the projection work in this particular way, but I also have to provide the structure group that contains all of the possible transition functions, or that in principle, I guess this way to say it is, I have to give you a structure group that captures the core essence of all of the transition functions, right? The structure group itself can be made very small by specifically choosing a very clever, the most clever possible or the most efficient possible local trivialization or atlas. So I can choose a very simple atlas, but ultimately the simplest atlas I choose has to at least have transition functions that are part of the structure group. And that's going to keep the atlas from getting so simple that all I do is create a massive trivialization for the total space. What prevents me from just saying that every total space for every fiber bundle is just the Cartesian project of B cross F is that ultimately the atlas that we put on E, the bundle atlas we put on E, must have transition functions that match up with the structure group, and that's what we'll talk about next time. All right, so we've covered just a few things here. We've got the notion that you need to make all this work. We need our total space, our base space, our fiber, our projection. The projection has to follow a key set of properties, and sometimes the projection itself is called the fiber bundle, and it's written this way in a lot of books. But the projection is definitely a map from the total space to the base space, and we know that the inverse projection of any element of the base space is a diffeomorphic to the fiber. And that will get you almost all the way there. The last thing you need is the structure group. And the structure group is a group G, which actually gets added up here as one of the things you need. And that structure group will ultimately have to contain all of the transition functions for your fiber bundle. And in the next lecture, we're going to start examining how that actually works. But you need all of these properties. And the last one, the structure group, is the one we introduced the last, is that's the one that actually deals with these transition functions. And you can have the same total space, the same base space, and the same fiber, but a different structure group, and you will suddenly have a different tangent bundle. All right, so we'll do some examples next time. It's going to take a few lectures to get through it. I realize this was a long one.